Okay. Good morning, everyone. Let's get started. So first of all, just remember homework 4, I think. If you have a started, please start it right now. Again, the programming load is not heavy, but you might have encountered some problems in debugging. And so please start. According to our past experience, some students might have problems when they try to call if you're using Python, we suggest using SciPy optimization package. I think that constraint optimization is called SLQP or something like that, right? So some students might feel a little bit unclear or doesn't have a clue about how to tune that, right? So if you need some help, please go to the office hour early. And also regarding the final project report, so yeah, we want to emphasize again. So for the final project report, there won't be any extension, neither personal extension or in whole class extension. The reason is just because we are required to submit your final grade by some hard deadline. The upper administration never give us an extension for that. That's why we cannot grant any extension for final project report. Okay, so yeah, please don't request for that. Right, I always receive several requests for extension. Even some students missed the deadline, even the late window, and then say, okay, can I get some extension? But for final project report, no, we cannot do that. Okay, so let us continue with the neural network. So today our major task will be go through the detail about backpropagation algorithm again to ensure everyone feels comfortable and feels no obstacle to implement by itself. Because last homework, the final homework 5, which might come next Tuesday or next Thursday, which is just about implementing neural networks. And so I think it's really important for us to get clear about every detail about backpropagation, and also from the idea from mathematical derivation to the implementation. So so today our major task is to go through the example discussed in the last lecture again. Then we wrap up the neural network topic with some practical, with some discussion from practical perspectives. Okay, so we talked about if we naively compute the loss function for a neural network, right? If we want to compute this gradient with respect to some particular edge weight, right? So now the naive approach would be, okay, for example, if I want to compute the loss L, partial loss L or partial WMNH. Remember, WMNH means the weight that stays at an edge that connects neuron M in layer H-1 to neuron N in layer H. Right? That's our definition of the notation. So if we naively compute this, we're gonna look at the destination node this edge points to, right? And then search for all the paths from this parent node to the root node or output neuron of the neural network. Right? Then from the output neuron of the network, we have pointed to the loss function, right? So loss function, you can view it as a virtual node because loss function is a direct function of the output neuron. Right? Then what shall we do? Any thought? You were just trying to stimulate our memories. Right? What shall we do? Look, look at this figure. What shall we do? Yeah, can anyone give me a guess? Yeah, if you want to compute partial L over partial W MNH. Okay. Can be more specific? Uh-huh. Yeah. Yeah, but how do we apply the chain rule? Yeah. When we get this path, how do we apply the chain rule? Mm-hmm. Uh-huh. Uh-huh. Mm-hmm. Yeah. Mm-hmm. I mean, we haven't yet talked back to the back propagation. Just talk about if we do the chain rule directly and naively, what should we do? I suppose from Z and H, we got three paths connecting to the output neuron Y and then to the loss node L, right? And if we apply the chain rule naively, how do we compute this partial derivative? Partial L over partial W MNH. At yeah. So basically, we're gonna first for each path, we're gonna multiply all the partial derivatives from L to Z and H, right? And then multiply partial Z and H over this W M N H, right? So get the result along one path. Right? Now we're gonna do this multiplication along every path and adds up the three products, right? That's what this giant expression does, right? Right. This is a new way of doing calculation of the gradient, right? So you can imagine if for a modern neural network, you might have 1 million weights. And every weight, if you're doing this, right, you just track what how many paths from the parent node to the output neuron, then to the loss function node, right? So many paths will be overlapping, right? Will be duplicated. That means you have to repeatedly compute many things. Does it make sense, right? Like suppose you got another neuron connect to Z and H as well. Like let me denote it by Z WM prime and H, right? It also on edge pointing to Z and H, right? So I have to go through the paths from Z and H, all the paths from Z and H to Y and L again, right? So it's really a big waste of computation, right? If you just apply the chain rule naively. Does it make sense? Right? That motivates our thinking about more efficient methods, right? So by efficiency, I mean, we just need to calculate what we have to do, right? Once something we have computed, we just catch it smartly. We never recompute. Right? That's the K motivation of backpropagation. Any question before we proceed to backpropagation? Is everyone clear about this motivation? Okay, so now let us revisit the example we talked about in the last lecture, right? So I'm gonna clear this page, right? I'm gonna redraw this neural network and do the backpropagation step by step again to let us go through everything, right? So suppose I got a layer neural network, right? Each hidden layer contains 3 neurons, right? It's a fully connected neural network. That means each neuron connects to every neuron in the next layer. Okay, this is layer 0, which is input layer, layer 1, hidden layer 1, hidden layer 2, and layer 3, which represent output neuron, the output layer. So this is X0, X1, X2, are just input features. And layer 1 is Z01, Z11, Z21, Z02, Z12, Z22. Sorry, 22. The more clear. Does it look clear for everyone? Do I need to enlarge the figure? No need? Okay. So what is backpropagation like? The framework is as follows. So backpropagation means that the computation order will from the output layer all the way back to the input layer. That is why it's called backpropagation. Right? And in contrast to during the prediction, we call the forward pass because we calculate from the input layer to the output layer. But when you do the backpropagation, you actually calculate from the output layer to the input. That is why it's called backpropagation. Right? And we're assuming that you have a loss function, which is just a square loss. So that means I can create a virtual loss node, which starting from the output neuron to the loss. Right? So, and backpropagation just calculate each layer and then move to one layer below, right? So in every step, the goal is to compute the partial derivative of the loss with respect to all the neurons in the current layer and with respect to all the weights on the edges pointing to those neurons. For example, in layer 2, the goal is to compute the partial derivative of L with respect to all the neurons in layer 2, which are Z0, 2, Z1, 2, and Z1, 2, and Z2, 2. Right? And then compute the partial derivative of L with respect to all the weights on the edges pointing to these neurons. That means those edges, right? Right? So you can imagine this is weights. There's the weights. There are weights. Those weights are on the edges pointing to the 3 neurons here. Right? So this is a task for each layer or each step. Right? Oops. And the calculation is not based upon or not leveraging the naive application of chain rule. Actually, it's based upon the calculation results in the previous step. So remember, in the previous step, we have already get the partial derivative of L with respect to all the neurons. I mean, the layer above, right? So we're going to leverage those results to calculate the partial derivative with respect to neurons in the current layer. And then with the weights associated with the current neurons. That's the idea. Does it make sense? Any questions so far? Okay, then let us pretend ourselves to be some robot, right? Let's just do it manually, right, by ourselves. So we're starting from the output layer, as you mentioned, right? That means layer 3. Right? So as we mentioned, is step 1, right? We're computing, our goal is to compute the partial derivative of the loss with respect to the neuron in this layer, right? So what neurons are in this layer? Yeah, there's only a single neuron, which is y, right? So we just need to calculate partial L over partial y, right? And also the weights on the edges pointing to the neurons in the current layer. Where are those weights? How many weights do we have? 3 weights, right? Because there are only 3 edges pointing to y, right? From the layer above, from the layer below, right? So that will be W 0, 1, 3, W 1, 1, 3, W 2, 1, 3, right? So that means we also need to compute partial L over partial W 0, 1, 3, partial L over partial W 1, 1, 3, partial L over partial W 2, 1, 3. Okay. So let us just do it. Right? So first, how do we compute partial L over partial Y? How do we compute that? Yeah. Because L is just an immediate function of Y, right? Or direct function of Y. And we know the form of L. So the computation is just straightforward. Right? So partial L over partial Y equals to Y minus Y star, right? So here, L is a direct function of Y. Right? You just do the partial derivative. Right? So then we're done, right? We're done with the partial derivative with respect to the neurons. Right? And then how do we compute the partial derivative with respect to every edge weight? How to compute it? Yeah. Okay. So this is a key observation. Look at those weights, right? They are all associated with Y, right? In other words, they're directly depends on Y. Oh, in other words, we should say it reversely. Y directly depends on them, right? And W013, W113, W213, they combine together to compute Y, right? So if we want to compute any of these partial derivative, we're gonna apply the chain rule, right? Partial L over partial W013 is partial L over partial Y, right? Partial Y over partial W01. Right? So you can see that you just read out the result you computed, partial L over partial Y. The partial derivative with respect to the parent node, the destination node that each edge points to. And then you compute the partial of the destination node with respect to the edge weight. for every case, all the three cases, they have the same structure, right? Partial L over partial W113 equals to partial L over partial Y times partial Y over partial W11. So partial L over partial W213 is partial L over partial Y is partial Y over partial 213. Does it make sense? Right? But here the key observation is that every edge weight actually only depends on the destination node its edge points to, right? So what you need to do is that, okay, I'm gonna read out this partial derivative with respect to the destination node, here's Y. And then multiply the partial Y over the weight, partial weight, right? So you can see that because partial L over partial Y has already been computed, you don't need to recompute. What you need to do is just to compute partial Y over partial of each of the three weights. Right? These are different, right? You cannot avoid. There's no duplication here. Does it make sense? So if you want to compute partial Y with respect to every edge weight here, we need to know what's the relationship between Y and those weights, right? So what's the relationship? Yeah, can we just read out this the expression? Yes, right. So this is a special for the output neuron, right? The output neuron is just a linear combination of the input neurons from the second last layer, right? So when Y equals to W013 times Z02 plus W113 times Z12 plus W213 times Z22, right? And now what is partial Y over partial W013? What's it? It's just Z02, right? Just read out the term it multiplies to, right? Which is just Z02, right? This one, what is this guy? Z12, right? What is this guy? Read it to me. Z22, right? So now multiply each of these with partial L or partial Y, which we have already known. We have finished computation, right? Does it make sense? Okay. It looks silly, or it's too straightforward. As long as you can implement the algorithm to do this automatically for you, yeah, that will be great, right? But here, I mean, even it's so simple, we need to figure out every detail. Okay. So now we have finished step one. We finished computation of partial loss with respect to all the neurons in layer 3, which is only one neuron, Y, right? And the partial L with respect to all the weights on edges pointing to neurons in layer 3, which is just Y, right? There are only 3 weights, right? And we figure out that the partial L with respect to every edge weight, it just need to multiply the partial L with respect to the destination neuron, then multiply partial destination neuron with respect to the weight, right? So this is very, very important, right? In output neuron, this might be very, very simple, right? But when you move downward, right, you will see how it can address, can avoid duplications. So now let us move to step 2, right? So step 1 we have done. Step 2 means that, okay, we're gonna move to one layer below, which is layer 2. And what's the task in layer 2? What's the task? Or step 2? What is our goal in step 2? Yeah, but what kind of things we want to compute in step 2? And with input. Remember, if you just want to compute the derivative with respect to the weights, that's not sufficient. That won't give you an efficient computation mechanism. Yes, right. So remember the K step, right? The K for every step is to compute. First, compute the partial derivative with respect to each neuron, and then use that to compute the partial derivative with respect to the weights. Right? That's very, very important. Okay, so how many neurons do we have in layer 2? 3 neurons, right? Z02, Z12, Z22, right? So that means we need to compute partial L over partial Z02, partial L over partial Z12, partial L over partial Z22, right? And then with this neurons partial derivative, we compute partial derivative of L with respect to every edge weight on edges pointing to these 3 neurons, right? How many edges point to the 3 neurons? How many? I heard that. Can you speak loudly? 9, right? So quite a lot, right? I'm not gonna enumerate them all, right? Let me just write it in a succinct way, right? It will be partial L over partial W I J 2, right? Because the target layer is layer 2, right? And we know that I J belongs to 0, 1, 2, right? Both the source neuron and destination neuron, their indexes from 0, 1, 2. Right? So now let us look at how do we compute this, right? So we're gonna first compute partial L with respect to every neuron in layer 2. Okay. So if we want to compute partial L over partial Z02, how can we do that? Yes, right? That's still kind of like straightforward, right? So here, I want to emphasize that we're gonna take the wheel of L in terms of function of the neurons in the layer above. So here, we take L as a function of the neurons in the layer above, which is output neurons, right? Which is Ly, right? And then we can use chain rule to compute the partial L with respect to the current neurons. Why do we take such a wheel? Yes, since computation, since we want to leverage the partial derivative with respect to the neuron in the layer above, right? Because I just computed their partial derivatives, right? We don't want to go all the way back. For example, you have many above layers, right? I don't want to leverage the results above that. I just want to leverage the results on the layer just one level on top of me, right? And so I don't need to backtrack to the whole path all the way up, right? That's the key idea. That's why we should take the loss function as a function of the neurons in the above layer of the current layer. Right? In the above layer of current layer is just the output neuron, output layer, right? So that's why we still will L as function of Y. Then we see that, okay, if we want to compute partial L with respect to every neuron in layer 2, we just first calculate partial L over partial neuron in the layer above, right? Then times partial Y over partial Z02. Does it make sense? Any question? Everyone feels comfortable? Right? Similarly, you can compute the partial L over partial Z12 as partial L over partial Y, right? Times partial Y over partial Z12. Partial L over partial Z22 equals to partial L over partial Y times partial Y over partial Z22, right? And again, we can see the benefit of catching the partial derivatives in the previous step, right? Because I already catched the result of partial derivative for the neurons in the layer above, one layer above, right? Which is partial L or partial Y. I don't need to recalculate, right? We just read out the results. You might think like, okay, this is look, because partial L or partial Y just Y minus Y star is very simple, right? But if you consider your loss is very complicated function, you still will like you catch this partial L or partial Y will be beneficial because you won't need to compute it. You just memorize it. So this part, just reading from the previous result, right? And what you need to do is just calculate partial Y with respect to every neurons in layer 2. These are something new, right? You cannot avoid. You have to compute. And this is relatively easy, right? You know that Y is just a linear combination of Z02, Z12, Z22. Just read out the coefficients, which are just the weights, right? Okay. So now we have finished the computation of the first part in step 2, partial L, with respect to every neuron in layer 2, right? And then we want to leverage this result to compute partial L with respect to every edge weight on the edge pointing to those neurons in layer 2, right? How can I do that? Let's pick a random pickup edge weight, right? So suppose I want to compute the partial derivative for this edge weight, which is 2, 2, 2. Right? It connects Z21 in layer 1 to Z22 in layer 2. That's why the subscripts are 2, 2, right? From 2. And the superscript is the index of the target layer, right? So how do we compute partial L over partial W 2, 2, 2, right? How to do that? Can someone just read to me? Yeah, that's the naive computation, right? So now we have already computed these results, right? Can we just leverage the results we just computed to get partial L over partial W 2, 2, 2? Yes, right. So it is a partial L over partial Z22 times partial Z22 over partial W222, right? Does it make sense? Right, because W222, this particular weight, depends only on Z22, right? It doesn't depend on Z12, Z02, or directly dependent on the neurons above, right? So that means if you want to compute the partial L over partial W222, you can just read out the partial derivative with respect to the destination node this edge points to, right? And then multiply the partial destination node Z22 over partial W222. Does it make sense? Any question? It's really straightforward, right? And similarly, how do we compute the partial derivative with respect to this edge weight, right? This guy should be denoted by W1, 2, 2, right? How do we compute partial L over partial W1, 2, 2? Okay. Someone raise it to me. Yes, right? Just looking at the destination node, right? The parent node. And then read out its partial derivative. Then multiplying with the partial destination node over partial target weight. Right? That's it. You can see that because those partial derivative with respect to the destination neurons have already been computed and catched, right? You don't need to recalculate. You just read it out, right? And what you need to do is just the right terms, right? Those are brand new. You have to compute. No way to avoid it. Any question? Hey, let us just do one more. Do one more practice, right? So what if I want to do this, right? So this edge weight will be denoted by W0, 1, 2, right? In case you don't see it clearly, right? So what if I want to compute partial L over partial W 2, 1, 0, 1, 1, 0, 1, 2. Sorry. Anyone can raise me how to compute that? Okay. Just read it. Okay. Right? Just straightforward, right? And you can use this way to compute all the partial derivatives with this 9 edge weights, right? Okay, so let us just review how to compute partial, say partial Z12 with respect to partial W012, right? This actually have been discussed in the last lecture, right? How to compute that. We need to know how do we compute this intermediate neuron, right? So we know that it is Z12 is what? How to compute? Yeah, activation function over the linear combination, right? So the activation function, inside activation function is a linear combination of the neurons from the previous layer, right? So that will be W0, 1, 2 times Z01, right? This guy. And this guy, which is W1, 1, 2 times Z11 plus W 2, 1, 2 times z 2, 1, right? Then if we want to compute partial z1, 2 over partial w 0, 1, 2, we're gonna what are we gonna do? How do we conduct the same thing? Yeah. Yeah. Oh, I'm just asking, like, how do you according to this relationship, right? This is how we compute z1, 2. How to according to this relationship to compute partial z1, 2 over partial w 0, 1, 2. I mean it's fine. Right? If you know, just let me know. Yeah, exactly, right? So you're gonna will this guy as a whole, then you apply the chain rule again, right? So suppose this guy is denoted by h, right? So that means partial z1, 2 over partial w 0, 1, 2 is partial z1, 2 because the sigmoid function outside, right? So it's partial sigmoid over partial h, right? Then times partial h over partial w 0, 1, 0, 1, 2, right? And h is just linear combination. So this guy will simply be a z 0, 1, right? Which is the who multiplying with w 0, 1, 2, right? And then partial sigmoid or partial h, we have already talked about how to compute that. If you don't choose sigmoid as an activation function, then you take the partial derivative of that activation function with respect to the input. So now, following this simple rules, we are able to compute the non-partial derivatives, right, for the non-edge weights pointing to z0, pointing to the neurons in layer 2. Any question? So you can see the rule is simple, but now the work amount increased a lot, right? You have 3 neurons to calculate their partial derivatives, and you have non-edge weights to calculate their partial derivatives, right? Okay, so suppose we finished step 2, right? The next step, we're gonna move one more layer below, right? We're gonna move to layer 1. Layer 1, right? That's step 3, right? Now I want to ask again. In step 3, namely at layer 1, what are we gonna do? Right? What results we want to get? Anyone just read to me? Z01 and then and yeah, I mean, we're talking about the results we want to get, right? In addition to partial derivative with respect to those neurons, what else? Yes, right? Remember, every step we want to compute 2 portions of results, right? One portion of results are partial derivative with respect to neurons. The other results are partial derivative with respect to weights on the edges pointing to these neurons, right? After all, our goal is to compute partial derivative with respect to weights because that's the neural network's parameters. That's the gradient I want to get, right? So again, in step 3, we're going to compute partial L over partial Z 0, 1, right? Partial L over partial Z 1, 1, and partial L over partial Z 2, 1. Right? Once we have obtained the results for those neurons, we're going to leverage them to compute partial derivative L with respect to the associated edge weights, right? Which are just Wij1, right? The target layer is edge 1. Those are weights on those edges, right? Still have 9 edge weights, right? Ij belongs to 0, 1, 2, right? Okay. Now let us look at how we compute the partial derivative of L with respect to every neuron first, right? So first, if we want to compute partial L over partial Z 0, 1, how can I do that? Anyone read it to me? First, we're gonna take the L as a function of whom? Function of what? No, it's not for Y. We're gonna take a collapse view of the function of function L, right? So as we mentioned, right, every time we're gonna view the loss function as a function of the neurons in the above layer over the current layer, right? So current layer is layer 1, right? The above layer is layer 2. So that means we're gonna view L as a function of neurons in layer 2, right? So which are L Z 0, 2, Z 1, 2, and Z 2, 2, right? And now we take this view to calculate partial L over partial every neuron in layer 1, right? So now who can tell me what is partial L over partial Z01? No, I'm not gonna add in a pass. Because right now, we're will L as a function of Z02, Z12, and Z22, right? So now if I want to compute the partial L or partial Z01, directly apply chain rule, what can we get? Now remember, if we just trace back the path from Z01 all the way to L, that actually costly, right? I just want to use the results in the previous step in layer 2 to compute for Z01, right? That's why we're gonna view L as a function of neurons in layer 2 only. Yeah, it's kind of similar, kind of like right direction, but can you speak it in a precise way? How do we compute partial L or partial Z01? Mm-hmm. As we mentioned, like if we apply the chain rule naively, right? We're gonna look at, okay, how many passes from Z01 all the way to L, right? But now we're not doing that because that will be too costly. So look, we have know that L is a function of these three neurons, right? Mm-hmm. Yes, exactly, right? That's why we say, okay, we should take the collapse view of the function of L, right? The function L now is viewed as function of the neurons in layer 2 only. You don't need to worry about, okay, how Z02, Z12, Z22 are connecting back to L, right? And according to this, right, we just straightforwardly apply chain rule. Right? So it will be partial L over partial, the first input to L is Z02, right? Is here. Then times partial Z02 over partial Z01, right? Plus partial L over partial second input, which is second neuron in layer 2, which is Z12, right? So partial Z12 times partial Z12 over partial Z01, right? And then plus partial L with respect to the third input is here, right? Which is partial Z22 times partial Z22 over partial Z01, right? You see that? It's just a direct, all right application of chain rule, right? We never think about, okay, we're gonna starting from Z01 and see how many hops we're gonna arrive at L, right? Because just will L is an immediate function of Z02, Z12, Z22, and apply the chain rule. The benefit is that, okay, when we directly apply this chain rule, we know this guy, this guy, and this guy, namely the partial derivatives with respect to all the neurons in the above layer has already been computed, right? Has been cached. You just read it out. Right? The partial L with respect to this neuron, with respect to this neuron, with respect to this neuron, have already been computed, right? You just read it out. And what you need to do is just to calculate what is every neuron in layer 2 is partial derivative with respect to our target neuron here, right? Because all the three neurons in layer 2 are related to Z01, right? That's why you need to compute the partial Z02 over partial Z01, partial Z12 over partial Z01, partial Z22 over partial Z01, right? Any question? Sounds reasonable to everyone? And similarly, how do we compute partial L over partial Z11, right? This node. How do we compute that? Yes, right? Because remember, that's why it is important to take L as an immediate function of the neurons in the above layer. Because we can directly apply the chain rule and leverage the results computed in the previous step. So computation is almost the same, except that the new partial derivative, we're gonna plug in changes a little bit, right? So it's now becomes now it becomes 0, z11, z11, and z11, right? And you can do the same thing for partial alpha over partial z 21, right? And what you need to do is, okay, you're going to read out the partial derivative for every neurons in the one layer above, which we have just computed in the step 2, right? And then multiply this actual dot product, right? With the partial derivative of every neuron in layer 2 with respect to partial derivative of the current neuron, right? And then multiply them together. In this way, you can compute partial L with respect to every neurons in layer 1. Any question? Does it make sense? Right? That's why this algorithm is so efficient. Because we're not gonna look at, okay, how Z01 connect to Z02 and then connect to Y and then connect to L and then multiply the partial derivative all the way along this path, right? We just look at one hop from Z01 to the neuron in the above layer. That's it. Because all the results up to layer 2 have already been computed. And we don't need to recompute it. Okay, so then once this 3 partial derivatives are done, we can use them to further compute the partial derivative for every edge weight, right? That is straightforward. That is exactly the same as we did in step 2, right? So again, to strengthen our impression, we just take some example, right? So suppose we want to compute this edge weight, right? Pointing from x1 to z11, this edge weight should be denoted by w111, right? How do we compute partial L over partial w111, right? Anyone can read to me? Anyone? Right? You just look at the destination node, right? Destination node will be z11, right? Because this weight is only dependent on z11. Right? That's why you can just read out the result we just calculated, right? Here, partial L or partial z11. Then calculate the partial z11, this parent node or destination node, over this partial of this weight, right? W111, and you get it. Right? And similarly, for example, if you want to compute edge weight, this should be denoted by W02, sorry, W011, right? So how do we compute partial L over partial W011? Right? Anyone can read it? Anyone? What's the destination node? Yeah. The destination node is still Z11, right? So that means you just read out the results. Partial L with respect to partial Z11. And then you do the partial Z11 over partial W011, right? So you do the same thing for every edge weight here, right? So then you compute partial derivative of L with respect to every edge weight, right? So now we finish step 3. Then we move to layer 0, which is input layer. That means we finish the computation. Then we're done. The back propagation is done. Okay. So you can see that at every step, we compute the partial derivative with the neurons first, and then use the partial derivative with the neuron to calculate the partial derivative with respect to the edges. And you do it layer by layer, all the way to the bottom, to the input layer. Then you finish computation of the partial derivative with respect to every edge, right? Then you finish computation with respect to the finish computation for the gradient, right? Because what we want is partial derivative with respect to all the edge weights. Right? This is the backpropagation. Any questions so far? Right? I mean, this is actually the foundation of all the modern neural network library, what they're doing. Right? And you might, in the future, you might be able to see a lot of like very fancy, very weird, all kinds of architectures, right? Their computational procedure, a logic, all follows this simple procedure we haven't shown you, right? They just make a little bit more complication tricks on top of that. They call it computational graph, whatever. But essentially, they're building such a procedure and compute it in a backward way. Okay, any question so far? If you feel uncomfortable, I guess for some students, they might still feel uncomfortable or even are not able to catch up this. This doesn't matter. We spend a lot of time going through step by step. Is just to give you a chance to practice by yourself. Right? In our homework, we'll also ask you in the written portion to list every step by yourself. Because we believe that only we can manually list every step, you can show that you're clear about this, and then you'll feel comfortable to implement with Python or whatever language you want. Okay. So to summarize, right, the backpropagation algorithm is just a repeated application of the chain rule for partial derivatives. It first performs forward pass from input to output and then compute loss. And then from the loss, proceed backward to compute the partial derivatives over the nodes, the neurons, and the weights using the chain rule. Right? And it relies, the computation will only rely on the partial derivatives over the neurons in the one layer above, that is in the previous step. Right? Then you can leverage that to compute partial derivative over the current neurons and weights. And then you do it layer by layer until you reach the input layer. That's the procedure. Thank you. So backpropagation enables us an efficient way to compute the gradient and enable stochastic gradient for the training of neural network. But backpropagation can be viewed as a general way to compute the gradient for composite functions. That's why right now, like when you see the deep learning libraries like PyTorch, like JAX, like TensorFlow, all those kind of stuff, you're not only restricted to neural networks. Right? You can specify any loss function, any structure of your model, and they can do this for you because they're gonna put this composition hierarchy will as a chain, right? Then they compute the gradient from the outer hierarchy then into the inner hierarchy. That's so-called backpropagation until you reach at the initial starting point, right? This and they call this as a computational graph. But there are some other ways to compute this efficiently. Sometimes they call it forward computing the graph. That means when I do the forward computing loss and also accumulate the gradient, then when I compute the loss, I get the gradient. So some libraries can support both forward computing and the backward computing. And forward computing has its own advantages, but in most cases, people will favor backward computation. This is out of scope of our discussion. Okay. So now once we have used backpropagation to compute the gradient of the loss for any randomly sampled examples, then we can get our stochastic gradient, and then plugging out our stochastic gradient descent framework, we can drive the learning of our neural networks. Okay, I think the last thing we want to talk about are the practice or practical concerns of neural networks, right? So the stochastic gradient descent is not the ultimate solution. They also have some issues, right? So that means in practice, people when they apply stochastic gradient descent to train a neural network, they also combine with other tricks, right? The major trick is how do we prevent overfitting, right? And also we need to think about how do we choose the architecture of neural network. Those are kind of like hyperparameters of neural networks, right? So because the neural network objective function is highly convex and highly nonlinear, so that means it might contain many of local minima, right? So we don't want our neural network to converge to a bad local minimum, right? We want to find a good local minimum, right? Might be give you an even smaller loss function, right? So, but stochastic gradient descent cannot tell you which local minimum it's gonna converge. That's why in the practice, many large networks are trained on large amounts of data, and also they're trained many times to find which local minimum is better. And then that means you have to run a lot of epochs, right? That means you have to go through the data for many times. And large data sets will therefore require many hours of CPU or GPU times, right? Sometimes specialized hardware even will be needed. For example, Google has designed their own computing unit. It's called TPU, tensor processing unit, to make it faster than GPU, right? Or some other large companies, they want to build up or design their GPU cloud because data is so large, one single GPU won't be sufficient to handle that, right? So they want to build up a cloud of GPU, and they want to load all the data into the GPU cloud, and there's no exchange between CPU and GPU and between GPU and memory, right? To make it even faster, right? So that relates many hardware problems. For example, the large language models, ChatGPT, they cannot be trained on some small computer labs. And if that's interesting, if you take a look at news, right, released by OpenAI, they said that they train the whole ChatGPT model for once will spend about $39 million. Right? That's really burning money. So another problem of using stochastic gradient descent is that it's hard to determine when we shall terminate. Right? We know that, okay, one common use way to determine if you converge, you just look at the gradient, right? If the gradient is 0. But for stochastic gradient, that's not released. Why? Because if you are able to compute the exact gradient, why should I compute the stochastic gradient? Right? That means it is because computing the exact gradient on the full data set is so expensive, so costly. That's why I want to avoid it. I want to approximate with some stochastic random gradient, right? That means if I really want to test if I converge to some local minimum, I cannot directly compute the gradient because it's too costly, right? So in practice, people use a variety of different heuristics to decide the end of the SGD epochs, right? For example, you can just specify the maximum number of epochs. Or you can look at the training set error and set a threshold. Or you can you can select a bunch of examples to form validation set, right? You just look at when the error on the validation data set is no longer decrease. And to avoid bad local minimum, we might try several runs, and each runs with different random initialization of those neural network weights and run, and then we'll either pick up majority training or voting techniques to get more robust results. Okay. And running SGD too long will cause another problem, which is called overfitting. So we know that the data set could be noisy, and even today you got very large data set, because neural network is even a larger scale, right? So you train a model, you feed data too much, there's still risk of overfitting, right? That's why in practice, to avoid overfitting, people won't run too many epochs. Right? They're gonna invent some strategy to stop early. So this strategy is called early stopping. Right? So what does we typically do early stopping, right? So we first keep a holdout validation data set, and then we run every a few epochs. For example, every 10 epochs, I will examine, okay, what is test accuracy, right? And then once I run, I find that the test accuracy does not improve anymore, I will just stop. I will pick up the current or the model parameters from the previous epoch as my results. This is called early stopping. This is a very important technique to prevent overfitting. And nowadays, like people in practice, nearly always use early stopping. Or you can keep running to a very large number of epochs, but I maintain weights for best performing network on the validation set. Right? Maybe I just run like 1 million epochs, right? And then I just report the performance after every epoch. And also I need to store the learned model weights, right? And then I look at which epochs, which may be just 1, 2, 3, 4 epochs, right? 1,234 epochs, I arrive at the best performance, and then I just read out the corresponding model weights, right? Doing this is also good, but it will need a lot of memory to memorize those learned results. And someone may feel like, okay, if I exclude a portion of data and use them as holdout data validation data set will cause us to lose some data information, right? What if I want to leverage all the data information? Right? Then a natural strategy will be used cross-validation, right? Or k-fold cross-validation, as we discussed before, right? We partition the data set for multiple folds, right? Every time I use one fold for testing, all the remaining folds for training, I do it for every fold, and then use the average accuracy as the index or measurement of the current choice, right? And finally, we'll pick up the hyperparameter choice, which gives the best cross-validation accuracy. Then I keep that hyperparameter choice and train our model on the entire data set. Right? This can avoid us losing any data information, but it is way more costly. Right? It is way more costly. If you just held out one data set and just monitor the performance on this data set and train the remaining, you just run once, right? If you use k-fold cross-validation, you have to at least run k+1 times, right? It's really, really costly. And another common used trick to avoid overfitting, is called dropout. Right? Was proposed by Geoffrey Hinton in 2012, and several years later, Google even filed a patent for this. They don't allow you to use it with some business purpose. That's very interesting. Right? So the idea is during the training, for each step, we're gonna use some probability to randomly decide whether we're gonna delete a hidden neuron. And once I compute the forward pass, right, I got my prediction, and I can compute, I can calculate the loss, right? Then I can run backpropagation all the way back and only go through those reserved neurons. We're gonna discard those deleted neurons. Then I finish one update. And in the next epoch, I'm gonna randomly delete another set of neurons and then do the forward pass and calculation of loss and backpropagation. And when we finish the computation, we finish the training, we use all the neurons to make prediction. So it works surprisingly well in that it can avoid overfitting and tends to have a model averaging effect. So there are like tons of papers discussing the mechanism that try to explain why it works well. Okay, so eventually to deploy the neural network, right, we also need to decide the architectures, right? So how many number of hidden neurons should we use? How many layers should we choose, right? So here is the rules of the thumb, right? Too few hidden units will prevent the system from adequately fitting the data and learning the concept. That means you cannot make your neural network to be too small, right? However, if you use too many hidden neurons, it can easily lead to overfitting, right? So we might need some cross-validation method to determine appropriate number of neurons and appropriate layers in your neural network architecture, right? So one hot research direction in the past few years is called automatic machine learning. The work is mainly about how do you automatically select the architecture for neural networks. Okay, so now we have finished up our discussion about neural networks, right? So we have given a definition of neural networks. We talk about how we use neural network, how we design neural network, how we use neural network to make prediction, and most importantly, we talk about how we train a neural network efficiently. So here, the key method is the so-called backpropagation. Okay. So, but all of our discussion is very, very fundamental. The neural network domain is a vast area and fast moving. Right? And every day there are many new algorithms and tricks for learning are proposed, and how do we tweak the gradient-based method? How do we use more advanced stochastic gradient descent approach, right? And also there are a lot of different architectures proposing every once in a while, right? And to solve problems, right? So well, hopefully our discussion will pave a way for you guys to dive into this more frontier, more cutting edge topics about neural networks. Okay, let's stop here today.